So we're happy to continue the morning session with a talk from Alex Ochirov on color decompositions from Unitarity.
Well, thanks to the organizers for inviting me to speak at Amplitudes again. And I want to talk about color structure of gauge theories, which is not necessarily a very hot topic now, but I'm still tempted to tell you about our results that we've obtained with Ben Page, because I think that, well, some of you who have computed gauge theory amplitudes and have ever had any problems with color structures, especially going beyond pure glue, hopefully will profit from this talk, and we'll think that color is even simpler maybe after this talk than it was before. So the main aim of this talk is to present you some flexible color decompositions of this form where I've at tree level I'm denoting a color dressed amplitude with a color graphic A, and I want to expand it in some basis B in terms of colored ordered amplitudes without calligraphic script and with some color factors. And I describe this kind of decompositions as being, by definition, I want to always fix two particles, here 1 and n, to be next to each other in the color ordering. And this is allowed by the KK Kleist-Coif relations displayed here.
Excuse me for interrupting, Alex, but there seems to be a green rectangle overlaying part of your screen.
You've seen it as well? Oh, that's too bad.
So,
yeah, it's weird. I didn't have it before.
Mysteries of Zoom. But maybe not. It's still back. Maybe you can just increase the size of your window. Go to a different mode. No, it's there.
Yeah. I'm on Linux. I don't know.
Try to go to full screen before you share.
Oh, stop share. And first go. Well, how do I do that? Yeah, and then share screen. Better now?
Well, now at least it's not on top of the transparency, so I think we can live with it.
Okay, great. So, yeah, sorry about that. These decompositions are the main aim of this talk, and by lines that don't have any, by just plain lines, I will be drawing any lines that could, or maybe scalars, just some colored particles. And a well-known example of such a decomposition is the Del Duca-Dixon-Moltoni decomposition for the pure Young males, at least. Let's consider the pure Young males here. It's a very explicit decomposition where the color factors in the basis, which is just, the basis is just the full set of permutations of the n-2 unfixed particles, and the color factors are just strings of structure constants, which can be displayed by half-ladder diagrams in the color Feynman rule terminology. So, well, this is a non-trivial fact that for pure gluons, we have this color factor here denoted here with a blob being actually equal to this half-ladder string of structure constants. And this is this kind of decomposition should be contrasted with the standard cyclically symmetric SUN trace decompositions, where the permutation goes over n-1 factorial, or that could be improved by a half, but not much better otherwise. And here I will be always drawing Feynman rules for color, which means that all the gluonic vertices are basically just structure constants, and all of the vertices with arrows are some general representation generators. So, for example, in this language, the basic color algebra, the Jacobian and the commutation relations are written just as presented here. And I will not actually be using the SUN completeness relation. It underlies the color ordering. This is how we define the color ordered amplitudes in the first place, but the color ordered amplitudes are kinematic objects. So once we have them, we can dress them with color factors in any other gauge group. So I will only be using the basic color algebra in this talk. So now that we've done with the preliminaries, I want to spend most of my talk talking about the color decompositions with flavored matter, and then hopefully have time to talk about applications to loops. And I will also be considering all matter to be separated into distinct flavored pairs, because of course, whenever there's a couple of pairs being of the same flavor, you can decompose that into the distinct flavor case. So this is an example of 4 quarks, for example. And to really explain the idea behind this talk is I'd like to present you this example first. So let's just consider a 5-point amplitude with 2 quark pairs, so only one gluon and 2 quarks of one flavor and 2 other quarks of another. And I want to to present you a so-called quark gluon stretch, meaning that I want to fix 1 and 5 to be next to each other. So so the permutations of 2, 3, and 4 that I am allowed to have, there must be 3 of them, and I can really fix the basis just by considering the factorization limits. The color dressed amplitude on the left-hand side must have this 3 factorization limits being non-zero, and the only way to have them in a color ordered amplitude is to have 5 next to 4, 3, and 2 necessarily. And the ordering of the other particles is then fixed by different flavors not being able to cross each other. So factorization limits allow us to cross the basis for this unorthodox stretch, but then the same factorization limits can actually give us the color decomposition. And to do that, let's again consider this factorization limits. On the left-hand side, I actually drew the same color-dressed amplitudes in different ways, but of course, to each, by construction, to each of these factorization channels, only one ordered amplitude will contribute. So when I go to color factors, when I just set all kinematic factors to 1, on the left-hand side, I just get the color factors of each ordering. Whereas on the right-hand side, the factorized amplitudes will provide their own color factors. So I have, for example, a 3-point color factor and a 4-point color factor. And at this low point, I, of course, know them for sure. So I explicitly get my color factors from factorization. And you see that something similar to the half-ladder diagrams of the DDM decomposition occurs as well. In the 2 cases where in the first 2 cases. In the other case, I have something not exactly half-ladder-like. And so I get the full color decomposition. And the observations that turn out to be general is that, well, first of all, just the presence of factorization channels allows us to constrain the basis for color ordered amplitudes. Then the factorization also allows color recursion, assuming that we know the lower point color decompositions, which we knew in this case. And the Comb-like structures seem to appear unless in the factorized channel, we get a stretch by the quarks of the same flavor, which is this 3rd color factor, where we factorize 2 and 5, and the remaining one was the remaining color factor had 1 and 2 below. But luckily, the like flavor stretch is the most studied. The basis for this stretch was formulated by Tom Melia, and the color decomposition was we've obtained with Henrik 5 years ago now. And I don't want to bother you with really many details. It's a nice story about how the quarks know about some bracket structures. So it's really like every quark is a bracket of some color if they're flavored. But I'm telling you just that the basis is known and the decomposition is known. Here's the formula. It looks ugly, but it's only ugly because in this way it's easier to implement. There's also a way to understand it pictorially through this vertical ladder diagram sum. And the simplest way to present it to you maybe is to use an example again, which is the same example at 5 points with 2 different quark pairs. It's just that now I'm not pulling by 1 and 5, but I'm pulling by 1 and 2. And so the color factors are not half ladder, but they're known. And that's what they are. And you can really derive that from the formula, for the more general formula here. So now that we know already 2 cases, so one of them is the DDM pure gluonic gluon stretch. The other one is QQ bar stretch in general QCD, or I mean by quarks I always mean any other matter particle. So I want really a generic stretch as I advertised, and to get it, let's consider again factorization channels. So on the one hand, I want to have my endpoint tree level amplitude, and first I'm taking the factorization channel S1p, where p is some subset of the bigger set of muted particles X. So I have 2 color ordered amplitudes with p and r being still permuted. So I'm allowing this permutations by color decomposing these 2 color dressed amplitudes into two color decompositions multiplied with each other. And on the other side, on the other hand, I can take the same amplitude and first color decompose it, and then take the residue. And of course, the residue is a kinematic operation, so it only acts on the color ordered amplitudes here. So what I get here is a higher point color factor multiplied by 2 color ordered amplitudes with permutation sigma 1 and sigma 2, assuming that the sigma 1 and sigma 2 actually are a non-zero factorization limit of the original amplitude. And so I can equate these 2 ways of approaching the residue, and I get this equation where this operation UPR is some operation that basically tells me that some of the amplitudes of the ordered amplitudes have a 0 residue on this pole just because the ordering constrains residues, and some of them won't, and I only pick those that have a non-zero residue. And the punchline of this talk is basically that once I can identify these permutations here, pi and rho, with sigma 1 and sigma 2, I get the color factors for free from factorization, as was already evident from the lower point example before, but now this is like a more general framework for that to happen, and this more general framework relies on something that must hold for the bases. So we call some lower point and higher point bases co-unitary if this set theory equation holds. But what it really does is that it picks out the factorization channels being 0, non-zero. And the minimal example of that happening or not happening is here at 4 points, where this amplitude is just one diagram. And of course, I just write the same thing twice in different, just turning it by 90 degrees. But considering it as a 1/4 stretch, I can cut it in between 2 and 3. And I do get a color factor from this factorization in terms of 3-point factors. Whereas if I consider it to be a 1/2 stretch, which is this like flavor stretch that we considered before, I cannot really cut it between 3 and 4, because then I would be cutting through, and there's just no such intermediate particle P with the right quantum numbers. And this is the problem that happens for QQ bar stretch, but then that is previously solved. So that's fine. We can actually construct everything now. And this slide may be too technical, but just for you to have some set theory equations telling you that, okay, we know what we're dealing with, and this is basically to allow you to code this very easily. And now we have we can present 3 new bases. So I also presented the melee basis in the same notation. And the main result, the main point of this basis is that, in contrast to the melee basis, where only quark brackets had to be chosen to be of one signature, you had to stick to, say, quark, anti-quark, always being in this order. But now we should allow flips of quarks also contributing to the basis. And you can see that we get the same, this basis, if you count the number of terms in this basis, you always get the same length as Méliès basis, which has to be the same, because we are color decomposing the same amplitude, just with different stretches. So for proof, you can look at our paper. I want to just tell you maybe pictorially what the color factor looks like. Imagine you're pulling by now 2 quarks of different flavors. You can just always, for any permutation sigma, you can always find a place where the first flavor was going out and the second flavor was going out as well on the other side, and then factorize. And everything in between, you can also factorize down. I could have let it just recurse, but I chose to factorize it maximally to show you that this color factor, which is new, is now given in terms of color factors that were previously computed, the DDM color factors, and the color factors from our paper with Henrik. And this is an example with 6 quarks of different flavors, where you again see that the small non-letter pieces occur whenever you have some enclosed brackets. And similarly, we can obtain color decompositions and the basis, and then the color decompositions follow for QG and GG stretches. So and these formulas are not really unique. You can factorize any way you want, because it will always factorize in ladder-like components, where sometimes you have, instead of a full ladder, you have some more complicated structure. So to summarize the tree-level story, now we have different allowed stretches, but they're all intertwined by mutual factorization. And once the amplitude bases are chosen co-unitary, all the decompositions but the QQ bar stretch are implied by factorization, that with factorization channels that have one n being separated. But and the fact that we knew already this color decomposition allows us to recurse very easily and write closed form formulae. So now I still have some time to tell you about how you could use that for to address loops with color. And the reason why I even thought about these things being useful at loop level was when we worked with Simon, Gustav, and Donald on this two-loop amplitude in pure Yang-Mills. So we just had this problem at some point where we had numerators, but we were not sure what color factors went with them. And this is the problem that comes to you when you use unitarity methods. Feynman diagrams have their color given to you by Feynman rules, so it's trivial. But with in the unitarity method, sometimes you get confused with trivialities like color. This is this full amplitude written for you in this notation. This is pure Yang-Mills, so all lines here are gluons, and these deltas are numerators, kinematic numerators, and the C's are again color factors. And this method works very seamlessly with unitarity within the integrand reduction framework, where every time you see some topology, a numerator topology or a cut topology, you can just blow it up with color factors of the that look like half letters. And this is in pure Yang-Mills, but now that you know how the story generalizes to general gauge theories, you can imagine that, for example, at one loop, you can only have three types of vertices occurring in topologies, and now you know how to color decompose the numerators, or rather, how to color dress the kinematic numerators once you have them from cuts, from color ordered cuts. And some examples here. As an example here, I can show you how bubble color dress numerators color decompose for an amplitude that has 2 quarks and n-2 gluons on external legs, but can have anything in the loop. So whenever you have a bubble loop being purely gluonic, you can just use DDM. But then when it's not, there is a quark. Well, it has to be quark of the same flavor as externals. So you're using this new QG, but it's not that new. It's really like half-letter DDMs, but with the line going through it. But then if you also allow different flavors of quarks being in the loop, there's something interesting happening that you have, this flavor can be the same flavor as the externals, and then you have this DDM-like color structure. But at the same time, there is a possibility of having so-called NF contributions from flavors not necessarily being equal to 1, to the flavor of 1 and 2, and then you have this other color factor. And the funny sign here, so the sign is with the sign is the fermionic sign that actually should take care of this closed fermionic loop. Of course, for scalars it wouldn't be there, but for quarks, imagine that it's there. It's actually automatically given by. Oh, okay, I'll have to go too far back, but it actually, the sign will then be given automatically through this through this factorization framework by the flavor decomposition of the tree level amplitude. If the tree level amplitude has a correct sign there, then the sign will propagate into the loop calculation seamlessly. So to summarize, I think I'm being well on time. To summarize, the trail level story is that now we have fully flexible classical reduced color representations. You can now not only stretch by 2 quarks of the same flavor, oh, that's me, but also different flavors, or quark and a gluon, or 2 gluons in presence of other quarks. We're reusing previously known results to our benefit, and of course, such decompositions can be then by color kinematics be used for gravity matter amplitudes. I love this paper by Jan and Vadim. And at loop level, you can use it via generalized unitarity method, and that's why Enrico pointed to me in his talk on Monday, and it's actually what's already implemented in the so-called Freiburg group numerically unitarity framework. So I'm happy that it's already been in use, and the story is absolutely orthogonal and somehow hopefully complementary to the normal, more standard SUN trace methods. And I hope that it will simplify future calculations beyond leading color at group level. So thanks a lot and stay safe.
Thank you, Alex. Let's actually give Alex a live round of applause, please. Some questions. So let's actually start with Lance.
Hey, Alex. Great talk. Looks very nice. If you go back to your very first example with the 5.1, it looks like the decomposition is not symmetric under exchange of the 2 quark pairs. Is that right?
Yes, it's not.
And so can you say more generally, you know, how much you have to break the n factorial symmetry when you have n different fermion pairs in the decomposition? Or, I mean, do you just have to pick out one of them and the other ones are symmetric, or is it sort of, does it have to be more broken than that? Or is that?
Well, I mean, the decomposition just breaks this symmetry, of course. It's just as the QQ bar would as well. You always, in this story where you break the cyclic symmetry of the color ordering, you want to minimize the number of ordered amplitudes that you even have to consider, or cuts if you're talking about loop level, and you just you fix 2 particles next to each other, and that always breaks the symmetry, if that's what you.
But maybe some of the other pairs aren't broken. The
other pairs, no, yeah, the other pairs will not be broken. The ones that are not fixed, they will be treated on the equal footing. So,
okay.
Yeah.
Thanks.
Actually, there's a question from Henrik. Henrik?
Yeah. Okay, good. Thanks for a nice talk. So I'm wondering, at one loop, so I suppose you have you must have a basis of fully reduced color factor at one loop, right? So the question is, what are the kinematic? I mean, what are the amplitudes that corresponds to this basis? I mean,
no. This way, when I propose to use that at loop level, I don't really say anything about those loop level color factors being independent. Their color, they are allowed to be linearly dependent. In fact, I mean, this is an overkill. This is just a way to consistently dress numerators. And
yeah, I guess I can understand that at higher loops, but I mean, at one loop, it's relatively simple to find a basis, both of the color factors and of the amplitudes, right?
That's been done.
But you cannot do it with this approach, or?
You can. You can actually. Let me just say. So for example, for this 2-loop calculation, this impressive group that actually did the integration of the integrand, when they integrated it, they reduced everything to traces. So once you construct your full color integrand in this way, you're allowed to do whatever you want with it. I'm not saying that you have to stick to those color factors in any way. It's just a nice, just a consistent way to construct things. But once you, so these are backup slides. For example, in the pure glue case, the DDM paper already has a one loop decomposition where they kind of glue things over the loop, the tree level DDM. And this is this decomposition, and we can really land on it through the through this approach. You can just and it's the non-trivial part of it is the symmetry factors. Because in the color addressed, in the color ordered one loop amplitude, there are no symmetry factors like in this formula. But if you were to start with a color, if you were to start with numerators, that would be 1/2 in front of some bubbles, but they just go away. So you can map it back very nicely to the original DDM, for example.
The follow-up question was, of course, if you have some intuition, what is a basis at 2 loops and higher? Because that's the hard question, like a nice basis.
Well, I think it's been solved by Nasulich and Edison in the pure gluonic case, and I wouldn't even, yeah, I don't think it's known beyond the pure adjoint theory.
Thanks.
All right, let's thank Alex again. There's a live round.